It is a familiar image, a majestic spiral galaxy filled with billions of stars slowly swirling around a dense, glowing core. For decades, we have viewed these structures as giant solar systems, where a supermassive black hole sits in the center and acts as a gravitational weight, holding the entire disk in a stable orbit. That model fails the moment you calculate the forces involved. A black hole's gravitational pull is immense in its immediate neighborhood, but it drops off rapidly with distance. By the time you reach the stars at the outer edges of a galaxy, the central black hole's direct pull is negligible. The outer galaxy is actually held together by the collective gravity of billions of stars, wrapped in a massive, invisible halo of dark matter. The black hole is a localized heavyweight. It cannot physically explain why the galaxy functions as a single, unified structure. This chart tracks the M-sigma relation, correlating a central black hole's mass with the velocity of stars thousands of light-years away. Notice the upward trending line. Gravity cannot explain how a localized mass dictates the precise behavior of stars at this immense distance. It suggests a connection that transcends simple attraction. Early computer simulations of galaxy formation made the problem even more obvious. When building virtual galaxies using only gravity and gas physics, the simulations consistently generated galaxies much larger than any we see in the real universe. Gravity alone fails to account for galactic structure. There is a galaxy-wide communication mechanism connecting the center to the furthest edges of the disk. To find that connection, we have to look away from the black hole itself and toward the highly volatile environment just outside its event horizon. As matter falls toward the center, the conservation of angular momentum forces it into a spiraling frenzy called an accretion disk. This is a colossal plasma whirlpool, wider than our solar system and spinning at significant fractions of the speed of light. The friction within this disk heats the matter to millions of degrees, converting mass into energy with terrifying efficiency. This creates a quasar, an engine that can outshine the combined light of every star in its host galaxy. A black hole's power comes from this radiated energy. It exerts influence through the catastrophic forces it actively fires back out into the galaxy. This process is known as feedback. It is the method the black hole uses to project energy and manage its surrounding environment. The first tool of feedback is the relativistic jet. These are focused magnetic cannons that fire particles at near light speed, piercing through the galactic core and traveling for hundreds of thousands of light-years. Then there is radiative feedback. The sheer pressure of the light from the accretion disk pushes outward, creating a physical barrier that can stop new gas from falling into the center. Finally, mechanical winds create galaxy-wide shockwaves. These winds physically push star-forming molecular gas completely out of the core, stripping the galaxy of its growth material. Jets, radiation, and winds transform the black hole into an active governor of its territory. This feedback serves a specific purpose. It regulates the galaxy's supply of cold, dense gas. Because gas must be cold to collapse and form new stars, managing this temperature is the key to controlling the galaxy's growth. A galaxy accumulates cold gas, triggering star formation and funneling fuel into the black hole. As it feeds, unleashed feedback heats the gas, halting star birth. The black hole starves itself, feedback turns off, and the gas slowly cools to restart the cycle. This thermostat mechanism dictates the lifespan of the galaxy, preventing it from consuming all its star-making fuel in a single burst. The galactic thermostat accounts for the M-sigma relation and the inaccuracies found in earlier simulations. Because the black hole and the galaxy's stars share the same gas supply, the feedback loop forces them to grow in tandem. When the black hole shuts off the gas to stop its own growth, it simultaneously stops star growth, mathematically locking their sizes together. When astronomers added this feedback break to their cosmological simulations, the virtual galaxies finally matched the sizes and structures we see in our telescopes. The connection uniting the galaxy is a shared, self-regulated climate. The black hole's influence reaches even further, impacting the massive clusters that contain hundreds of individual galaxies. Jets from a single dominant black hole can heat the gas across millions of light-years of intergalactic space, suppressing star formation in dozens of neighboring galaxies. This relationship is visible throughout the history of the universe. Cosmic star formation and black hole activity mirror each other, rising to a peak together 10 billion years ago and declining in unison to the present day. Supermassive black holes function as the active architects of their domains. They shape, govern, and ultimately sculpt the empires of stars that surround them.